Hello everyone. In this second session of this week, so I will keep continuing my discussion about this classification method. In the last session, we have looked at the univariate LDA with only one input variable. Here, we will extend it to multivariate LDA with more than one variable. For more than one predictor, a random vector x with x1, x2, xp, p random variable is assumed to be form a joint Gaussian distribution. So this joint Gaussian distribution is noted by mean vector mu and covariance matrix sigma. Here, mean vector mu is actually the vector of expectation of x1 and expectation of x2, blah blah blah, expectation of xp. This is a mean vector. And actually, this covariance matrix is given by expectation of x times x transpose. So another way to say it, this is a big matrix P by P, big matrix with the 1,1 element is the expectation of x1 and x1, which is a correlation, or the x1 expectation of the x1 square. Then next one is the expectation of x1 and x2, and blah blah blah. Last one is given by expectation of x1 and xp. And so in this way, the last element is expectation of xp square. So this is the covariance matrix. Okay. You may remember that a univariate normal distribution is given by 1 over 2 phi sigma square times exponent of minus 1 over 2 x minus mu times 1 over sigma square times x minus mu, like this. Okay? If we rewrite this one, it is 1 over 2 phi of to the 1 half times sigma. Okay? So this is the PDF of the just normal distribution. In the other course, Mathematical Foundation course, you have already seen the PDF of a joint Gaussian with two random variables, or bivariate joint Gaussian. You may remember that the PDF of the bivariate Gaussian is quite complicated. In general, the PDF of multivariate Gaussian can be expressed by in this way, especially using the matrix notations. Here 1 over 2 phi. Here p is the number of the variables, or size of the random vector x. Sigma between this the vertical bars. Sigma between these two vertical bars. This one means the determinant of this covariance matrix. So it is the square root of the determinant of the sigma, which is very similar with this expression. Then we have exponent term, this x minus mu, which is also similar to the univariate case, and inverse of the sigma, which is similar to the 1 over sigma square, and another x minus mu, which is similar to this one. So basically, even though it uses a matrix form, basically it follows the PDF form of a normal distribution. Usually, the multivariate normal distribution is visualized like this, and each marginal looks a normal distribution Two random variables are somewhat correlated to each other here. Okay, so here, as like we did for univariate LDA, we can similarly find the discriminant function. Compared with the discriminant function of a univariate LDA, we can see this formula is a very similar form. Just using vector notations. This is a function of a vector x. Only the first term with this x. And this is the x transpose times some multiplication with another vector. So this is this discriminant function is linear function to this x. The decision boundary can be obtained by putting discriminant function of two different classes to be equal to each other, which is this is the decision boundary is at the point that delta k of x is equal to delta L of x. This such x can be found by this equation, which is this equation. Then by solving out this equation, we can see this is the solution is also a linear function of x. That means the decision boundary is also linear function. This is the illustration of LDA with two variables, x1 and x2, and with three classes. Samples from three classes are distributed in this way. One is from here, the other is from here, the third one is from here. Okay. They are modeled to be generated from three different joint Gaussian distributions. A joint Gaussian distribution is expressed as an ellipse, like this. Because the x and y are correlated. Usually, x and y are correlated well, like this. The shape of three Gaussian should share the same covariance. Okay, so the shape of these three ellipses are identical, except each centroid. It is because the three joint Gaussian share the same covariance matrix, and only the central points are central points means its mean. Central means points are different. The decision boundary is found by points where values of two PDF functions are equal to each other, which is like this boundary, this line, or this line, or this line. So the decision boundary can be expressed as such dotted lines. So any point in this area is classified with this the light blue, and any point within this range is classified with this the dark blue class. Okay, so up to now we have discussed about the LDA. Then next, move to the SVM, the support vector machine. SVM has a bit different approach from that of logistic regression or linear discriminant analysis. Logistic regression and LDA try to model the characteristics of samples in a class. Then they predict a given sample to that class, to the class which has the most similar characteristic with the given sample points. Instead, SVM focus on the decision boundary itself. SVM try to find the best decision boundary that distinguish two groups of samples very well, rather than finding the characteristic of each sample groups, just like LDA or logistic regression. Okay, so basically, SVM finds a linear decision boundary that is expressed as a linear line. Okay, in a two-dimensional space with x1 and x2, a linear line is generally expressed by beta 0 plus beta 1 x1 plus beta 2 x2 is 0. So a linear line is generally expressed by in this way. How about in the three-dimensional space? In three-dimensional space, similarly, it might be expressed by beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 equal to 0. However, the set of the points that satisfy this equation is not a line. Actually, in three-dimensional space, it's a plane. Okay. Then, how about the four-dimensional space? We can express that line, a kind of a line, in a similar equation, but it's not a line. It's not a plane. So, however, it is still linear. So, generally, in a p-dimensional space, the linear decision boundary can be expressed by beta 0 plus beta 1 x1 plus blah 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 plus beta p xp equal to 0. It is linear, but it's not a line, it's not a plane. We call such a boundary hyperplane. So SVM finds a hyperplane for decision boundary. Definitely, there can be many hyperplanes that distinguish two groups of samples well. For example, in this two-dimensional space, with two groups of samples, dark one and white one, two hyperplanes are possible to distinguish two groups perfectly. One is like this one. The other is like this, the light blue one. Which one looks better for you? Intuitively, you think this one, this light blue one, is better because actually it has the larger space between these samples and here, and between these samples. Okay. So it is expected to be more tolerable to some small noise. Okay. The space from the hyperplane to the sample point, this distance is called margin. So different sample points have different margins according to its distance to this hyperplane or the decision hyperplane. So importantly, SVM finds a hyperplane that maximizes the. It's a little bit weird. SVM tries to find out a hyperplane that maximizes the minimum margin among the all margins. In other words, a hyperplane that maximizes the margin of the closest point. That is a SVM. Such a hyperplane can be found by this optimization problem. Here, yi times beta 0 something blah 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 blah. This whole stuff actually says this is a margin. This is actually the margin of sample I to the line, to the hyperplane. That hyperplane is when hyperplane is given by beta 0 plus beta 1 x plus blah 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 plus beta p and xp equal to 0. Okay. So this constraint, this inequality means for all samples, the margin should be larger than or equal to a certain value of m. Then in this setting, we want to find out this beta 0 and beta 1, beta 2, and beta p, then maximize this m. Okay? This is the optimization problem that includes the idea of SVM. Here we have one more constraint that the squares, the sum of the beta squares should be equal to 1. This is just the constraint to fix the scale of the data. Without this constraint, we can increase m as much as we want by scaling down this beta, right? Because the multiply alpha or divide by alpha to here, that's the same. Okay, so that's why we need this constraint. You can see this. You can see that this optimization problem depends only on the closest point. If the closest point have the margin larger than or equal to m, it is okay. Everything is fine. Here we say this closest point to the separating hyperplane actually supports this classifier. It's why this method is called support vector machine. However, in many cases, it's not possible to find such a perfect hyperplane that perfectly separates two groups of samples. For example, if the samples are located in this way, okay, in this way, let's think of this is the hyperplane, and this is the bounded the maximum margin. Okay, some of the samples are actually within the margin. To solve, to allow such a situation, we introduce soft margin. Soft margin allows some samples are more close to the hyperplane, or even it is on the other side of the hyperplane, like this point or this point. Okay, so in such a case, it's not allowed with the hard margin. Okay, so in this case, these samples that is on the other side of this hyperplane, they actually have negative margin. Definitely, we cannot allow soft margin too much. The amount of the soft margin should be limited, right? In SVM, we control the total amount of this soft margin. The hyperplane with this soft margin can be found by these equations. This is the optimization problem. It is similar to the previous one, but instead of this hard margin, they have a soft margin m times 1 minus epsilon I. The epsilon I is a positive term that regulates the soft margin of sample I. If this epsilon I is 0, sample I has a hard margin. If it is non-zero, sample I has a margin less than m. If it's larger than 1, it has a negative margin. The total amount of this soft margin can be calculated by sum of this, the epsilon i's, which is this one, right? And this sum is limited by certain parameter c. Actually, this c is a tuning parameter that controls the amount of violation or soft margin. Actually, large C makes the SVM model more flexible because it can fit more complicated data. So we can say C is also tuning parameter for the flexibility of SVM. Okay. So this is a support vector machine with soft margins. Up to now, we use a hyperplane to separate two groups of samples. A hyperplane is a linear boundary. Then how can you apply the SVM for the data with non-linear decision boundary? If data is located like this in this figure, definitely we can still use a linear hyperplane with the very large soft margins, right? With very large soft margins. However, it is inefficient. One of the general solutions is to introduce higher order terms like the x squared or x cubed and so on. Please recall the extension of the linear regression to polynomial regression. This process can be generalized, can be definitely applied to this SVM. Also, this process can be generalized using a kernel function. Kernel. A kernel is the data transformation. For example, data in two-dimensional space with x1 and x2, they can be transformed to the four-dimensional space of x1 and x1 square, x2 and x2 square throughout the polynomial kernel. If we can find a linear hyperplane on this the higher order, higher dimensional space, then we can get back to the the original data space. Then the hyperplane might not be linear anymore. Okay, so then let's see how these kernels can be applied to SVM. Believe it or not, the optimization problem of SVM in the previous slide is equivalent to this optimization problem, then minimizing this L of alpha. So believe it or not, this L of alpha includes a term of the xi transpose times the xj. This is just the sum of the multiplication of each element of data x vectors of sample I and sample j. If we include the higher order terms and transform x vectors, we just include more terms in this summation. Okay. But instead of this simple inner product function, the idea of the kernel is expansion is this idea actually use a general kernel function k of xi and xj instead of this the simple element-wise multiplications. So by defining this kernel function well, we can transform the data into the new data space and apply non-linear decision boundary. Here are kernel functions commonly used. Linear kernel is just the inner product. Linear kernel is just equal to the inner product. And the polynomial kernel is to introduce the higher order terms, and this is a polynomial kernel. And here, the exponent of d determine the highest order. So we can say the controlled flexibility of this the polynomial kernel. The most popular kernel is a Gaussian kernel or radial kernel, a radical kernel, which is defined exponent of minus gamma times the Euclidean distance between two vectors. This one is actually indicate the Euclidean distance between two points. Okay, between the xi and xj. Actually, if you apply some Taylor expansion to here, to this the exponent function, you can easily see that this function is the sum of the higher order terms with the decaying, exponentially decaying weight that is exponentially decaying by gamma. In other words, this radical kernel include infinitely many higher order terms, but their effects are getting smaller and smaller with increasing order of this gamma. So here, gamma is a control factor for the flexibility. Okay, here is the summary. Classification is a prediction problem for a discrete outcome output variable without an order. And logistic regression actually a linear regression model for the logic of the probability. And LDA is based on posterior probabilities, and SVM is a method that finds the hyperplane with the maximal margin, including the soft margin idea as well as kernel. Okay, so here are some references you may want to see. Okay, then I'm gonna finish up here. Thank you very much.